Good morning. My name is Doji. I am doing Masters of Statistics in the University of Wollongong. Today I am going to present on the topic Laplace equation, basically to find solution to the Laplace equation in a rectangle problem. My presentation outline is focused on introduction, difficulties in solving Laplace equation, and finding solution to Laplace equation to the rectangle problem, Fourier sine series, and references. So first, what is meant by Laplace equation? Laplace equation is a second order partial differential equation which is used to define gravitational and electrostatic potential and as well as steady flow of fluid and idle fluid. Laplace equation is widely used in the field of science and engineering because of its wide applications. It is used to solve electromagnetic problems. It is used to study the steady state heat problem and is used to determine the flow of fluid in fluid potential, and it's also used to calculate the electric and gravitational potential. It is represented by Laplace square u equals to 0, which is the Laplace equation, or Laplace and u equals to 0, and the Laplace operator is represented by Laplace square or Laplacian. So what are the difficulties in solving Laplace equation on a rectangle? So the difficulties is that unlike heat and wave equations, Laplace equation has to solve everywhere at once. For example, in a rectangle problem, to solve a Laplace equation, we have to solve on each side of the rectangle. On all the four sides of the rectangle, you have to find a solution to solve the rectangle problem. Second difficulty is that the boundary conditions are not homogeneous. So that's why they do not fully separate. Third problem is that the separation of variables always require homogeneous boundary conditions. So how to solve Laplace equation on a rectangle? The solution to the Laplace equation on a rectangle is obtained by using method of separation of variables and using superposition principles. To completely solve Laplace equation, we have to solve it 4 times on each side of a rectangle. Each time we solve it, only one of the 4 boundary conditions can be non-homogeneous and the remaining 3 will be homogeneous. Then, once we solve all 4 of these problems, the solution to the original system will be the sum of each solution obtained on the 4 sides of the rectangle. So this is the main original system or the problem of a rectangle which is subject to the boundary conditions, 4 boundary conditions here. So if you look at the problem, 4 problems of rectangle with the boundary condition, we have first case where we're trying to solve on the bottom side of the rectangle where we have non-homogeneous condition here and homogeneous condition on the other sides of the rectangle. And similarly, in this second rectangle, we're trying to solve on the right side of the rectangle with the homogeneous boundary conditions on all other sides. And with third rectangle, we're trying to solve the Laplace equation on the top side of the rectangle with homogeneous boundary conditions on the other side. And last, we're trying to solve on the left side of the rectangle by considering the homogeneous boundary conditions on the rest of the sides of rectangle. So once we solve all the 4 sides of the rectangle, then the solution to the original system for the whole rectangle is obtained by adding each solutions that are obtained on each side of the rectangle. So now how to find a solution to the left side of the rectangle? So on the left side of the rectangle, the PDE is given by this equation where the Laplace of u4 is equals to u of xx plus u of yy equals 0, where the x is bounded within the limit 0 to L and y is bounded with 0 to h, with the subject to boundary conditions where u0y is equal to u1 of y and other sides are homogeneous boundary conditions which equals to 0. So now how to solve Laplace equation on this right side of the rectangle using separation of variables. First, we presume our solution to be in the form of u4 xx equal to x of x and y of y. So by substituting into the Laplace equation, we get this equation, and dividing through by x of x and y of y, we obtain this equation where x double prime of x divided by x of x is equals to minus y double prime of y divided by y of y. Since the left hand side depends only on x and right hand side depend only on y, both must be a constant. So now we get our equation in this form where x double prime of x is equals to x double prime of x minus lambda x of x equals to 0, and y double prime of y plus lambda of y equals 0. These are the two quadratic equation. Now let us try to find the solutions for y of y and y of x so that you get the solution to the Laplace equation. So first case we consider when lambda is less than 0, what will be the general solution? The general solution to the y of y is given by a of e to the power lambda minus root minus lambda y plus b e to the power minus root minus lambda y. So by applying the boundary conditions, we get that y of 0 equals 0, where we get y of 0 equals to a plus b. This implies that b is equals to minus a. And we apply second boundary conditions where we have y of h is equals 0, then we get 0 is equals to b sinh of root minus lambda y. This shows that we can either have b equals to 0 or the function sinh of root minus lambda h equals to 0. Since the sinh function cannot be 0, the b should be equals 0. If b is equals to 0, then a is also equals 0. So therefore, the solution to the y of y is equals 0. Therefore, the solution to the original problem is equals to 0. So there is no non-trivial solutions. So it is impossible to find the value of lambda in this case. So next case is when lambda is equals 0, the general solution is given by y of y is equals to e to the power lambda y a plus b. When lambda is 0, we get e to the power 0y is equal to a plus b, which is equals to a plus by. So by applying boundary condition y of 0 equals 0, we get a equals to 0. And applying boundary conditions y of h equals to 0, we get bh equals to 0, where b is equals to 0. Then since a and b are equals 0, again we obtain non-trivial solution. So it is again impossible to find the value of lambda in this case. So now we proceed to the last case where we have lambda is greater than 0. Then the general solution is given by y of y is equals to a cos square root lambda y plus b sine root square root lambda y. So by applying boundary condition y of 0 equals to 0, we have a equals 0, and applying b of h equals 0, we get b sine of root lambda h is equals 0. Therefore, we obtain lambda is equals to n pi divided by h whole square. So therefore, now we obtain the yn of y, the solution to yn of y function is equal to bn sine n pi by hy. So next, what's the solution for the x of x? Since we got lambda is equals to n pi by h whole square, the solution to the equation of x double prime of x minus lambda x of x equals 0, the solution is given by x of x is equals to constant c e to the power n pi by hx plus constant d e to the power n pi by h. So this solution can be written in the form of hyperbolic trig function where x of x is equals cn cos n pi by h l minus x and dn sinh n pi by h l minus x. The shift in x by l is applied to satisfy the boundary condition at x equals to l. Now, if by applying boundary condition where u L of y equals to 0, we get that c of n is equals to 0. When c of n is equals to 0, this function is 0, and then we get x of x is equals to just this function, where you get our general solution for x of x, which is equal to dn sinh n pi by h L minus x. So now we find our general solution by combining the x of x and y of x solution, where it is equals to dn sinh n pi by h L minus x times sine n pi by h y for any constant dn where n goes to 1 to infinity. So now by using superposition principle, we obtain that u of xy is equal to summation of 1 to infinity dn sinh n pi by h L minus x times sine n pi by h y. So this is the solution to the Laplace equation with homogeneous boundary condition on other side of the rectangle, for which we have chosen for any real number constant given by dn. So now next question is, how do you find the coefficient of the solution, that is dn in this case? The solution to find the coefficient dn in this solution, we know by the fact that for any smooth function g of y, g1 of y with the condition g1 equals g1 of 0 equals g h of equals 0 can be represented by Fourier sine series. So therefore our g1 of y is equals to sum of n goes from 1 to infinity dn sine n pi by h y, where the y goes from 0 to h. So to find the coefficient dn of this solution to Laplace equation, first we have to know what is Fourier sine series. Since the Fourier sine series is used in finding the coefficient dn of this solution to Laplace equation, now we'll go through what is Fourier series. So Fourier series is an expansion of periodic function in terms of an infinite sum of sines and cosines. So Fourier series make use of the orthogonality relationship that exists in sine and cosine functions. So in this case, the Fourier sine series of a function fx on the interval minus L to L is represented by f of x is equals to sum of n goes from 1 to infinity an sine n pi x by L, where the x goes from minus L to L. Next, how do you find the coefficient an? So to find the coefficient of an, we know that the Fourier sine series converge to a function, so we can find the coefficient an in this homogeneous sine series. So firstly, we multiply both the side by sine m pi x by L on both sides of this equation, and integrate over the limit minus L to L, so which we get this equation. And then by using the calculus, we know that we can interchange the integral and the sum, and by factoring a n out, we get this equation. So now we apply the orthogonality property of the sine, where we get am, there's a coefficient is equals to 1 by L times integral of the interval from minus L to L of fx sine n pi x by L, and the constant coefficient am is also equals to 2 by L when the integral go from 0 to L for f of x sine n pi x by L for m goes to 1 to infinity. So to sum up, the Fourier sine series of a function f of x over the interval minus L to L is given by f of x equals to sum of n goes to 1 from infinity, an, the constant an, times sine of n pi x by L. We can find the constant an by using the orthogonality property of sine, where an is equals to 1 by L integral of minus L to L f of x, the function itself, times the sine n pi x by L dx. Or the coefficient an can be computed by using this formula, 2 by L when the integral go from 0 to L and the function is f of x and sine n pi x by L dx. So now, by going back to our original solution to find the coefficient dn, we said that using the Fourier sine series, the dn is equals to 2 by L, the integral from 0 to h g1y of sine n pi y by L then dy. So thus we obtain that dn is equals to dn divided by h sine sinh n pi L by h. So now our general solution to the Laplace equation to the left side of the rectangle in the equation 3 mentioned earlier, we get that the solution is u4xy is equal to summation of n goes from 1 to infinity dn sinh n pi by h L minus x times sine n pi by h y, where we compute dn, the coefficient, is given by this 2 divided by h sinh n pi L by h, where the integral goes from 0 to h g1y sine n pi y by h dy. So how do you find the solution for the other three sides of the rectangle? The solution to the Laplace equation on other three sides of the rectangle is obtained in a similar manner. So if you want to find the solution to the right side of the rectangle, then the solution is given by u2xy summation from n goes from 1 to infinity dn sinh n pi x by h sine n pi by h y, where the coefficient dn is given by this Fourier sine series using orthogonal property of sine series, where dn is equals to 2 divided by h sinh n pi L by h integral from 0 to h g2y sine n pi by h y dy. And similarly, the solution to the Laplace equation on the bottom side of the rectangle is given by u1 of xy, where summation goes from 1 to infinity dn sinh n pi h minus y. Here the h minus y shift is to find the value when h is equals to y. That's why we have the shift h minus y here. So it's equals to u1 of xy, where summation of n equals to y to infinity dn sinh n pi h minus y divided by L times sine n pi by Lx, where the constant coefficient dn is computed by using 2 divided by L sinh n pi h by L, where the integral goes from 0 to L f1x sinh n pi x by L dx. And finally, the solution to the Laplace equation on the top side of the rectangle is obtained by given by this solution, this equation, where u3xy is equal to summation n equals to 1 to infinity dn sinh n pi y by L sine n pi x by L, where coefficient dn is computed in this manner, where 2 divided by L sinh n pi h by L, where the integral goes from 0 to L, the function f 3x sine n pi x by L dx. So if we add all these solutions on each side of the rectangle, then we'll get the final solution for the whole rectangle problem. So this is how we compute or find solution to the Laplace equation to a rectangle problem using the separation of variables and principle of superposition. And these are the references I use for the presentation. Thank you.